Buenas tardes con todos, queridos amigos y amigas. Estamos listos para empezar la clase número 2. Estamos avanzando más rápido de lo que pensaba. Entonces, hoy vamos a ver todo el módulo 2 y vamos a avanzar igual con todos los videos que podamos. Les recomiendo tener a la mano un esfero, un cuaderno, para que puedan tomar notas. Estamos ya grabando esta clase, entonces vamos a compartir el link para que puedan verlo. Apenas esté listo, ¿no? Es más o menos una hora después de que terminemos la clase. ¿Ok? Entonces arrancamos. Que disfruten la clase.
Now that you've got a deeper understanding of what essential oils are and the basics of extraction processes, we're going to move on to essential oil chemistry. Once you understand the chemistry behind essential oils, you'll be able to use them safely and more effectively. First, let's talk about what chemistry actually is. Everything around you, from the air you breathe to the clothes you wear, is made up of different substances. And substances consist of tiny particles called atoms, which are made up of even tinier particles called electrons, protons, and neutrons. Chemistry studies substances at this tiny atomic level. There are a lot of different types of atoms, and how many electrons, protons, and neutrons an atom has determines what element it is. You've probably heard of elements such as, say, oxygen, hydrogen, and helium. The atoms making up these elements have different numbers of protons, neutrons, and electrons. Altogether, there are 118 different elements, all with unique combinations of protons, neutrons, and electrons. When two or more atoms link together, it creates a molecule. Water, for example, is a molecule. You've probably heard it referred to as H2O because it has two hydrogen atoms and one oxygen atom linked together. This molecule is what you drink to stay hydrated every single day. When it comes to essential oils, we focus on organic chemistry. Organic chemistry is the study of molecules that have carbon in them. If a molecule has carbon, it's considered an organic molecule. Carbon gets a lot of attention because it's so good at building molecules. It loves bonding with other atoms and is stable enough to make the complicated molecules necessary to create life. Without carbon, you can't have DNA. And then, where would we be? An important feature of carbon is its ability to make large or complex chains. These chains of carbon atoms are referred to as a carbon backbone. Other atoms will build on this backbone to create the whole world of carbon-based molecules. I'll talk more about carbon backbones in a few minutes. But now, let's take a look at a carbon-based molecule. Remember how we talked about the chemical compound linalool in lavender essential oil? Here's a basic diagram of the atoms that make up linalool. In this graphic, you can see the letters C, H, and O. These letters represent the different atoms in a linalool molecule. In this example, C stands for carbon, H for hydrogen, and O for oxygen. Another thing you ought to be aware of is the number of chemical bonds between atoms. This molecule has both single and double bonds, which are represented in this diagram by one or two lines joining the atoms. Don't worry about this too much, but it'll come up again later, and I want to make sure you have some background. The different molecules found in essential oils are what give them their therapeutic value and aroma. The chemical makeup of an essential oil affects how the oil interacts with your body. Each essential oil also has a different number of molecules. Wintergreen, for example, is almost entirely made up of one kind of molecule called methyl salicylate. Spikenard, on the other hand, has hundreds of different molecules. Few people truly appreciate the complexity of essential oils, particularly the oils that contain hundreds of molecules. Too much or too little of any given molecule can affect the aroma and properties of the essential oil. So, we've established what chemistry is and the importance of molecules in different essential oils. Now, let's take it a step further. Remember how we talked about how molecules are atoms linked together through a chemical bond? Well, if the atoms that are connected are different types of atoms, they are not only a molecule, but they are also a compound. Water, because it has both hydrogen and oxygen, is both a compound and a molecule. Ozone, which is just 3 oxygen atoms joined together, is only a molecule. Essential oils are filled with all different kinds of compounds. What these compounds have in common is that they are volatile. We defined what volatile means in the first module, but just in case you need a refresher, volatile means that a substance can change from a liquid to a gas really quickly. Now that you know what a molecule and a compound is, and you understand the importance of carbon in building compounds, it's time to really dive into the chemical structure of essential oils. Now here's something interesting. No 2 plants will produce essential oils with the exact same chemistry. Even 2 plants from the same species will have variations in their chemical composition. Many things can affect the chemical makeup of an essential oil, including the region the plant was grown in, the time and season it was harvested, and the quality of the soil. This means that the lavender grown in Bulgaria actually has a different chemical composition than lavender grown in the Himalayas. In the same species, however, the main difference between 2 plants is usually the amount or percentage of the major compounds for that species. For example, lavender from the Himalayas and lavender from Bulgaria will both have the compounds linalool and linalool acetate, but they'll have differing amounts. This is important to understand because, as we talked about earlier, the amount of any given chemical constituent in an oil affects the benefits of that oil. Sometimes the growing environment can impact a plant so much that it actually produces a totally different chemical composition. 2 plants can have the same genus and the same species, but diverge within the species into different subspecies, which scientists call chemotypes. Even though 2 plants look and grow the same, inside their chemistry is so different, they are categorized as a different chemotype. The chemotype of an essential oil is important because it can influence its effectiveness and safety. So, what causes plants to have different chemotypes? The chemical constituents of the plant are different because of minor changes in the makeup of their DNA and how the plant's genes are expressed. Think of identical twins, same DNA, but slight differences in their appearance. When we talk about the chemistry of essential oils, we start with something called terpene. This is a type of aromatic molecule created by plants. So, why are terpenes important? Well, out of the 3 different kinds of terpenes relevant to essential oils, monoterpenes, sesquiterpenes, and diterpenes, monoterpenes and sesquiterpenes are the main compounds present in essential oils. Terpenes are basically the building blocks of essential oils. Diterpenes are not frequently found in essential oils because they are heavier and don't easily evaporate during steam distillation. Monoterpenes have a 10-carbon atom backbone arranged in either a ring or a straight chain. They are found in virtually all essential oils and come in all different kinds of shapes. They can be circular, straight, or branched. They are also clear, fluid, and aromatic. Each possesses its own unique function. Monoterpenes are small, which means they react quickly to air and heat. Their small size also allows them to absorb better into tissue and fit through the small spaces of cell walls. Remember that monoterpenes have an easier time getting inside cells. Sesquiterpenes are heavier than monoterpenes. They have a backbone of 15 carbon atoms. Their larger size makes them less volatile, which means that they don't evaporate as quickly. This also makes it a little more difficult for them to cross through into cells, but they're still below the molecular weight that allows them to do so. Their superpower is their unique shapes, which allows them to adhere to proteins and activate receptors on the surface of cells. The fact that sesquiterpenes can interact with proteins is significant because proteins are what facilitate pretty much everything that happens in a cell, and cells are the building blocks of your body. So, sesquiterpenes affect proteins, which run the show in your cells, which impact the health of your body. An essential oil can have both monoterpenes and sesquiterpenes, giving it a broad range of benefits. For example, frankincense oil has both monoterpenes and sesquiterpenes, which allows it to interact with cells in a variety of ways, inside and out. In addition to terpenes, essential oil compounds have another molecular group called a chemical family. The chemical families are alcohols, aldehydes, alkanes, and so forth. The compounds that make up essential oils can be both a monoterpene and an alcohol at the same time, or a sesquiterpene alkene, or a monoterpene aldehyde, and so on. Think of it like sticking a chemical family building block on a terpene building block to make something new. Every possible combination of terpene and chemical family represents its own unique class of molecules. There are 9 main chemical families in essential oils, and I'll talk about each briefly. An alcohol is a molecule with a specific arrangement of atoms, an oxygen atom bound to the carbon backbone on one end and a hydrogen atom on the other end. There are multiple alcohols, but they all share the same group of atoms. It might be easiest to imagine alcohol molecules as a certain shape. Let's say a triangle. You can have different angles, but it always has the same basic structure, and anytime you see it, it's recognizable as a triangle. Each chemical family has its own basic shape, made up of a unique group of atoms. But back to alcohols. In general, alcohols have names that may start with the parent terpene they were derived from and end in -ol. Examples include menthol, geraniol, linalool, cedrol, cusamol, 4-terpineol, and citranolol. Keep in mind, you can have monoterpene alcohols and sesquiterpene alcohols. So, what do alcohols do for an essential oil? Essential oils with alcohols are known to serve as powerful cleansing agents, provide antioxidants, support restful sleep, support a healthy cardiovascular system, and provide an uplifting aroma. Not all alcohols have these exact properties, but these are commonly found in various alcohols. This principle is true for the other chemical families we'll discuss. Which essential oils contain alcohols? Oils that are high in monoterpene alcohols include tea tree, geranium, coriander, basil, jasmine, and lavender. Essential oils that are high in sesquiterpene alcohols include sandalwood, vetiver, cedarwood, and patchouli. Phenols, also sometimes referred to as phenolics, are a special subtype of alcohols. They are made up of an alcohol group, which, as we talked about earlier, is made up of oxygen and hydrogen attached to a benzene ring. Now, a benzene ring is made up of 6 carbon atoms arranged in a hexagon pattern with exactly 3 double bonds inside the ring. Phenols are very potent, and because of this, essential oils that contain phenols may cause skin irritation. Like alcohols, their names end in -ol. Common phenols include carvacrol, eugenol, and thymol. You can have monoterpene phenols and sesquiterpene phenols, but sesquiterpene phenols are not commonly found in essential oils. Essential oils containing phenols are known to offer antioxidants, aid immune function, and are cleansing. Essential oils that are high in monoterpene phenols include thyme, oregano, clove, cinnamon bark, cinnamon leaf, and basil. Aldehydes have a carbon atom that is double bonded to an oxygen and is also bonded to a hydrogen and a separate carbon in the molecule's carbon backbone. Aldehydes are unstable and susceptible to oxidation when exposed to oxygen and low heat, making it important to store them properly. This is important because oxidized oils will irritate the skin far more than non-oxidized oils. Oxidation can also potentially change the aroma and even the therapeutic benefits of an oil. They are known for their distinct, potent fragrances and are often key contributors to the overall aroma of an essential oil. Aldehydes usually end in an -al or aldehyde. Aldehydes commonly found in essential oils include cinnamaldehyde, geraniol, nerol, decenol, and cumanol. You can have monoterpene aldehydes and sesquiterpene aldehydes, but sesquiterpene aldehydes are not commonly found in essential oils. Aldehydes are known for several health benefits, including offering antioxidants and supporting healthy digestion and gastrointestinal function. Essential oils that are high in monoterpene aldehydes include cassia, cinnamon, lemongrass, melissa, and cilantro. Similar to aldehydes, ketones are molecules with a carbon atom double bonded to an oxygen atom and the carbon atoms flanking this carbon, not bonded to any atoms other than carbon and hydrogen. Most ketones end in -one. Examples of ketones include camphor, carvone, davenone, jadamazone, leptospermone, menthone, muscatone, and rotundone. Essential oils with ketone molecules may improve the appearance of the skin, support healthy respiratory function, and promote healthy digestion. Oils high in monoterpene ketones include spearmint, dill, peppermint, geranium, and caraway. Spikenard is an oil that's high in sesquiterpene ketones. The simplest organic molecules, alkanes, consist entirely of single-bonded carbon and hydrogen atoms. Few essential oils contain alkanes, and those that do typically contain small quantities. Examples of alkanes include nonadecane, henocosane, heptadecane, tricosane, icosane, nonane, undecane, pentadecane, and pentacosane. Essential oils containing alkanes are known to soothe the skin, promote relaxation, and are balancing and grounding. An alkene is a molecule with no chemical families present and at least one double bond between any two of the carbons on its backbone. They also have a large number of double bonds and structural rings, which makes them excellent receivers of unpaired electrons and free radicals. This is helpful because we don't want free radicals or unstable atoms bouncing around in our cells causing problems and breaking things. Alkene molecules usually end with -ene, such as alpha-pinene, beta-pinene, limonene, saponine, gamma-terpenine, germacrene D, beta-caryophyllene, zingiberine, and alpha-cedrine. Essential oils that include alkenes can help to rejuvenate skin, promote an uplifting environment, provide antioxidants, and support a healthy inflammatory response. Essential oils that are high in monoterpene alkenes include frankincense, Douglas fir, blue tansy, green mandarin, lemon, lime, pink pepper, red mandarin, tangerine, and wild orange. Essential oils high in sesquiterpene alkenes include ylang-ylang, black pepper, copaiba, melissa, and ginger. Esters are a chemical family that results from the reaction between an alcohol and a carboxylic acid. This reaction is called esterification. Esters have a central carbon atom double bonded to an oxygen atom, single bonded to the carbon backbone, and single bonded to a second oxygen atom. Esters are oxygenated compounds, which means that they have oxygen as part of their chemical structure. They also usually contain 2 carbon chains. Esters normally have 2-word names with the second word ending in -ate. Some examples of common esters are linylyl acetate, bornyl acetate, methylamyl angelate, methylthujate, methylsalicylate, and neryl acetate. You can have monoterpene esters and sesquiterpene esters, but sesquiterpene esters are not commonly found in essential oils. Essential oils containing esters are generally calming, relaxing, and balancing, reduce skin blemishes, and are soothing when applied topically. Oils high in monoterpene esters include lavender, clary sage, bergamot, jasmine, Roman chamomile, helichrysum, arbor vitae, and wintergreen. Sesquiterpene esters are not commonly found in essential oils. Ethers are molecules with an oxygen atom bonded on two carbon atoms. Those carbon atoms are bonded to either another carbon or a hydrogen. Ethers end in various suffixes, but many end in ol, like the most common, ether 1A cineol, also called eucalyptol. Other ethers include anisole, curzarine, and furanoeudesma 1,3-diene. Essential oils with ether molecules in them can help promote feelings of clear airways, improve the appearance of the skin, cleanse, and support proper immune function. Oils high in monoterpene ethers are cardamom, eucalyptus, rosemary, tea tree, and peppermint. Oils high in sesquiterpene ethers are myrrh and vetiver. Oxides are oxygenated compounds that include an oxygen atom and a part of a hydrocarbon ring structure. You can identify an oxide based on its proper name, which generally ends in either the suffix oxide or ol. Common oxides found in essential oils are eucalyptol, rose oxide, linalool oxide, caryophyllene oxide, and pinene oxide. You might notice that eucalyptol is also in the ether family. Because of their structure, it is not uncommon for some constituents to belong to multiple chemical families. Essential oils that contain oxides provide antioxidant support, promote a sense of clear breathing, aid healthy respiratory function, and are soothing to sore muscles. Oils that are high in monoterpene oxides include eucalyptus and rosemary, and oils that are high in sesquiterpene oxides include copaiba and melissa. Phenopropenes are molecules with a benzene ring attached to an allyl group, 3 carbon atoms and 5 hydrogen atoms. Examples include safrole, estragol, transanethol, elemicin, and myristicin. Unlike other chemical families that typically end in similar suffixes, phenopropenes can be difficult to recognize because they tend to have unique names. Very unique. Phenopropenes may support healthy brain and cardiovascular system function, provide antioxidants, and aid digestion. Essential oils that are high in monoterpene phenopropenes include fennel, myrtle, anise, star anise, and basil. Phew! That was a lot, but it's super important to get a grasp on the molecules that make essential oils work. Now that you got that stuff down, we will dive into how these molecules are identified and how to test for purity. purity of an essential oil is its most important characteristic. Using an essential oil that isn't pure means you run the risk of germs, plastics, heavy metals, or contaminants entering your body. These can cause irritation, adverse effects, or even illness. So, how do you know if an essential oil is pure? The answer's simple. Testing. Purity and testing go hand in hand because testing validates purity and potency. Quality testing ensures that every bottle of essential oil contains nothing but 100% pure and volatile aromatic compounds for maximum efficacy and safety of use. Unfortunately, as the market's demand for essential oil has continued to grow, so has contamination and adulteration. Both contaminated and adulterated oils result in products that are impure, less effective, and potentially even dangerous. Quality testing helps identify and detect contamination and adulteration before they can harm someone. Contamination is often, despite the connotation of the word, unintentional. It happens when impurities like heavy metals, plastics, and pesticides aren't caught and removed during the distillation or supply chain process. Thankfully, it is relatively easy to detect contamination through basic testing methods. So, how does an oil become contaminated? Contamination occurs when impurities inadvertently make it into a batch of essential oil. There are a few different ways this can happen. If the distillation or expression equipment isn't cleaned between batches, you could end up with lavender in your rose oil or mixtures of other oils extracted using the same equipment. High-quality distilling facilities have strict cleaning protocols in place to avoid this type of contamination. In addition to unclean machinery, contamination can often occur due to a lack of resources or proper equipment. For example, some plants are harvested and distilled by growers in rural areas and developing countries, where resources are limited. There have been cases when these growers distill plant material and collect essential oil in plastic soda bottles because that's all they have available. This isn't highly common, but it does happen. The problem with this practice is that some essential oils, for example, lemon, can break down the plastic of the soda bottle, which leaches plastic chemicals like plasticizers and phthalates into the oil, contaminating the batch. Contaminants can be introduced during the plant's growing process, such as pesticides sprayed on the plant or heavy metals present in the soil. Along the way, essential oils can be exposed to other substances and synthetic chemicals like chlorparaffins, which are chemicals used in paints, flame retardants, lubricants, and other products. Contamination can be avoided by carefully monitoring the process from beginning to end. Adulteration is the intentional inclusion of compromising substances, natural or synthetic, that affect the safety or effectiveness of a product. These can be found in essential oils as well as food, cosmetics, fuel, and lots of other everyday items. Common adulteration practices include adding isolated aromatic chemicals, substituting or adding less expensive oils, diluting with another substance, or adding synthetic chemicals. Unlike contamination, the adulteration of essential oils doesn't happen by accident. Adulterating an oil takes purposeful planning, and unfortunately, it can be difficult to detect. Basic testing can't always spot adulteration, and the untrained eye usually doesn't see it. So why would someone adulterate an oil? What's in it for them? Well, some essential oils are intentionally adulterated to increase the company's profits by lowering the cost and increasing the supply. Pure essential oils can be costly to produce, and unscrupulous suppliers might try to lower their costs by adding other substances to the essential oil. This can be done by diluting with vegetable oil or adding synthetic chemicals that were created artificially. Another adulteration tactic is to try passing off less expensive oils as rare oils or adding the cheaper oil to stretch the amount of the expensive one. Cassia instead of the more expensive cinnamon, or spike lavender instead of lavender. For example, lemongrass oil is widely produced and pretty inexpensive. It's similar to Melissa oil, which is one of the most rare and precious essential oils. It's possible to convince somebody who isn't trained that the lemongrass oil is Melissa oil, and then sell it for several times the price. Usually, adulteration is a result of brokers. Often the company may not even know that the oils they're selling are adulterated. They buy from a broker they trust, not realizing they're being duped because they don't have the resources or expertise to test for the most sophisticated kinds of adulteration. They unknowingly and innocently advertise their oils as 100% pure when in fact this is not the case. Now that you have a better idea of what adulteration is, let's talk about some of the specific methods that are used to adulterate essential oils. One of the most difficult kinds of adulteration to detect is the addition of natural isolated volatile organic compounds. Natural isolates are chemical compounds that are present in plants from the get-go, but they've been isolated and removed from their natural source, then added to an oil. Someone could also isolate, say, linalool from an inexpensive oil like hoe wood, and then add it to a more expensive oil such as rosewood. For instance, alpha-pinene may be extracted from turpentine in pine wood and then added to an essential oil that naturally contains alpha-pinene like frankincense. Turpentine is a byproduct of the paper-making industry. Alpha-pinene is easily extracted from it, which provides a natural source of alpha-pinene from trees that is then added to frankincense. Frankincense is 45 to 50 times more expensive than alpha-pinene isolated from turpentine. Detecting this type of adulteration requires a qualified chemist who has significant experience analyzing essential oils and a massive database built up over years of analyzing thousands of samples. Not many companies have these two important resources. Some essential oils are less expensive than others, so producers may mix two or more essential oils to cut costs. An example of this is the addition of lavandin to lavender essential oil, or the mixture of clove stem essential oil with clove bud essential oil. It's also possible that a less expensive oil has been substituted, for example, disguising cassia oil as cinnamon oil. We detect adulteration with natural isolates by carefully looking at the presence or absence of natural occurring volatile molecules and incorrect molecular ratios. Again, this takes expertise beyond the norm. Without expert-level testing, this type of adulteration often slips under the radar. Another method of adulteration is the addition of carrier oil like a castor oil or coconut oil to extend the essential oil, taking up space in the bottle. In some cases, a company might pre-dilute an essential oil with a carrier oil for those who want to avoid skin sensitivity. This is common and isn't considered adulteration because the company is being transparent about the contents of the bottle. The type of adulteration we're talking about here consists of adding a carrier oil to an essential oil and not listing it on the label, making consumers think they're receiving the full oil, not a diluted version. For instance, castor oil can be added to frankincense or patchouli in small quantities so that it's cheaper to produce. While this cuts costs, it is misleading. Someone might think they're using pure frankincense oil when, in reality, their bottle includes a great deal of carrier oil that simply looks like frankincense. Again, there are some cases when adding a carrier oil can be beneficial in order to avoid skin sensitivities. However, if a carrier oil is being added simply to cut costs and without the customer's knowledge, it's extremely misleading. Fortunately, the addition of carrier oils leaves obvious markers when tested. If a carrier oil has been added at any point in the production process, an essential oil company should be able to tell with the use of basic testing. One of the most concerning types of adulteration is the addition of synthetic chemicals because they can be especially harmful. Some naturally occurring volatile compounds are easily synthesized in a lab. Carvone, a major component of spearmint, and carvacrol, the primary component in oregano, can be synthesized from limonene. When these synthetic chemicals are cheaper than the natural isolate, they may be added to an essential oil. Synthetic chemicals, similar to their natural equivalents, are easily made from common petroleum products. There are millions and millions of tons of cast-off byproducts from the petroleum industry. From these cast-off byproducts, you can take raw material phenols and other things that come from gas and oil and, through simple chemical processes, turn into just about any chemical constituent. Wintergreen is a good example. Wintergreen essential oil is hard to produce, and it's not uncommon to pay a couple $100s for 1 kilogram of genuine wintergreen. Knowing that wintergreen essential oil is almost entirely methyl salicylate, some producers purchase synthetic methyl salicylate for less than $10 per kilogram and mix with small quantities of genuine wintergreen oil to sell as pure wintergreen. It smells exactly the same and would pass most testing standards, but you can tell through carbon dating that isn't pure wintergreen. Because it has been produced with petroleum products, carbon dating will show that it's actually 7 million years old, which obviously is too old to be from a wintergreen plant. Testing will also show the absence of naturally occurring monoterpenes along with identifiable markers. Again, confirming that it's a petroleum byproduct, not pure wintergreen. Another oil that's commonly adulterated with synthetic chemicals is lavender. This is because linylyl acetate naturally occurs in lavender in large quantities, and synthetic linylyl acetate is an easy compound to create. Turning a small amount of real lavender oil into a large amount of adulterated oil is a simple matter of adding the synthetic compound. Some essential oils like neroli and ylang-ylang may be completely reconstructed with synthetic chemicals. The creation of synthetic chemicals inevitably leaves markers or impurities that originate from the starting material. These markers may go unnoticed by the untrained chemist or a chemist who's not using a robust database with these chemical standards present. When testing for adulteration, a chemist needs to look at more than just the major constituents of the oil. Instead, she must know what to look for in each oil that indicates adulteration, because these show up in trace amounts often less than 0.5%. One example is peppermint and cornmint essential oil. If cornmint, Mentha arvensis, is treated to remove some of its menthol content, the chemist would see the major components of peppermint, menthol and menthone, in the right ratios. But when the chemist looks closely at minor components like isopolygol and methylfuran, she would note the telltale signs of the cornmint substitution. How we said that essential oil purity and testing go hand in hand? Now that we've discussed some of the ways that essential oils become contaminated or adulterated, let's talk about the testing methods used to detect those impurities. You'll remember that some types of adulteration and contamination are relatively easy to detect, while others can be more subtle and tricky to identify. Either way, to produce safe quality essential oils, rigorous testing is key. Not every essential oil company employs the in-depth testing methods required to verify that their oil is high quality. Testing takes time and costs money, so some companies skip this step to save on resources. Though there is some variation between companies when it comes to testing, there are a few testing methods that are considered best practices. Since there aren't clear industry standards for testing essential oils, we'll walk through the doTERRA Certified Pure Therapeutic Grade (CPTG) testing process as an example of how in-depth testing works. We'll explore a wide variety of testing methods and explain why each is important. Generally speaking, the testing process is looking at 4 different things. First, it needs to verify that the chemistry of the essential oil is correct. Second, it looks at the physical characteristics of the oil like its density, color, and even molecular structure to be sure the sample is an authentic essential oil. Third, it checks for contaminants. And fourth, the testing process makes sure the oil is stable and won't lose its efficacy within a certain amount of time. We've spent a lot of time looking at the chemistry of essential oils because chemistry is the foundation of pure, high-quality essential oils. There's actually a set of chemical standards for each type of essential oil. In order for a lavender oil to be considered true lavender oil, it needs to have the correct chemical compounds in the correct ratios. Each lab should be able to check the ratios and chemical compounds against their own database. After the aromatic compounds are distilled from the plant material, you'll need to confirm that each batch meets the chemical composition standards according to the essential oil database using a series of tests. It's best to conduct the testing with scientifically validated pharmacopoeia standards, which are established official publications that provide information about therapeutic solutions. In other words, the same standard of scientific testing used by qualified organizations. Perhaps you've heard the term GCMS while watching a crime show on TV. But what actually is a GCMS test and what does it do? Well, to put it simply, it tests a substance and tells you what it's made of. The test actually uses 2 different instruments. The GC stands for gas chromatograph and the MS stands for mass spectrometry. We are going to look at them separately to see the part each of them plays in a GCMS test. But first, here's an analogy that will hopefully help make more sense of how this test works. Essentially, the gas chromatographer separates an essential oil sample into its various compounds. It's like putting a chocolate cake into a machine and it comes out on the other side as a bunch of ingredients. Then the mass spectrometer analyzes those ingredients and tells you exactly what they are: eggs, flour, sugar, and cocoa powder. Yum. When used to test essential oil rather than to reverse engineer cakes, it separates an oil into its individual components and turns them into ions, which are electrically charged molecules. Once an oil has been broken down, the test can be very specific and identify exactly which volatile aromatic compounds are there and precisely how much of each compound is present. The gas chromatograph was invented in the 1940s and quickly became a highly used tool in analytic chemistry. The GC portion of the test is where the whole process starts. A sample of an essential oil gets added to the machine and is vaporized or turned into gas, hence the name gas chromatograph. This process of vaporization occurs in an inert carrier gas like helium. An inert carrier gas is used to make sure the vaporized essential oil gets where it needs to go, but doesn't affect the testing results. With the essential oil completely vaporized, it's ready to go to the next area of the GC machine, which is a hair-thin tube that has been coated with compounds that possess specific properties. Each of the aromatic constituents in the essential oil interacts with the tube walls in a different way. As a result, each individual constituent will elute or move through the tube at a different speed. A compound will move quicker if it has little interaction with the compounds coating the tube, or slower if it has a lot of interaction. A detector at the end of the tube identifies when and how much of a compound exits the tube. This provides a detailed report of which chemical constituents are present in the essential oil as well as at what levels. Once the oil sample is through the gas chromatographer, it goes in the mass spectrometer. I'm going to explain how this machine works, and it'll get complicated. But what you need to know is that this test identifies the exact chemistry of a compound. When the results come back, we can see exactly which chemical compounds are in the essential oil sample. It's like running someone's fingerprint to find out their true identity. The mass spectrometer contains 3 basic parts: a source of ions, a mass detector, and an analyzer. When the essential oil sample gets to this stage, it's already been separated into individual compounds by the gas chromatographer. Now it gets ionized. This means the compound is struck by a stream of electrons, causing the neutral molecule to break apart and become charged. These ions are then sent into a series of magnetic fields where they interact based on their molecular mass and charge. The instrument reads each constituent based on quantity, mass, and charge. The person running the test gets those readings and can tell exactly which compounds are in the sample. Once the GCMS test has verified that the sample of essential oil is what we thought it was, there are more tests that can detect adulterations and synthetic chemicals. One of these tests is called chiral GC analysis. Chiral is a word used in chemistry to describe the pattern in which some molecules are put together. Essential oils contain constituents with expectable distribution ratios of enantiomers, or a pair of molecules that are mirror images of each other. A chiral GC analysis can identify the distribution ratios of these different enantiomers. These ratios are important when testing essential oils because they can help us detect adulteration that has happened through the addition of synthetic chemicals. For instance, true pure Melissa essential oil should have an enantiomeric ratio of 99% of one kind of methylcitronellate and 1% of another type of methylcitronellate. Analyzing these ratios can help the chemist determine if synthetics have been added to a sample. An additional test that is used to detect the presence of synthetic chemicals, like heavy metals, is the inductively coupled plasma mass spectrometry, which is abbreviated as ICP-MS. This highly sensitive and versatile test is used to detect trace elements such as potentially dangerous heavy metals like lead, mercury, cadmium, and arsenic. It atomizes the essential oil sample to create atomic containing only one atom and small polyatomic containing more than one atom ions. The ions are the elemental form of the essential oil, and through this test can be detected with great speed, precision, and sensitivity. An essential oil sample is introduced into the instrument via a pump. The sample is nebulized into an aerosol that is transported by a plasma torch. Metal ions in the sample are subjected to intense heat and are transported from plasma through a vacuum interface into a mass separation device called a quadruple, where they're separated based on mass to charge ratio. This test quantifies the elements in the essential oil. Any sample that fails to meet specifications is rejected rather than sent out for secondary processing to remove the heavy metals. Once a batch is determined to meet chemical profile guidelines, it can move on to the next stage of testing.
Hola, buenas con todos. Bueno, espero que hayan podido aprovechar, disfrutar, tomar notas de esta clase. Me pareció impresionante, la verdad, todo lo que pude aprender. Increíble, hay un montón de información, hay que repasarlo varias veces y profundizar un poco más, tratar de... Bueno, esto fue por ahora. Mañana continuamos con la 3.7. y a la misma hora, ¿de acuerdo? Ya les voy a mandar la grabación para los que quieran revisar, más o menos en una hora que se demora en procesarse. Que tengan una linda tarde, que disfruten mucho y nos vemos mañana. Hasta luego.